Hello, everyone. In the previous lecture, we talked about magnetic vector potential, and now we're going to continue with that discussion. So let me review what happened in the previous lecture because that's very relevant to this lecture. We said let's assume we know current. And if you remember, for radiation, we need time variant current. So this is the current density that I'm writing here. Then after that, we're finding magnetic vector potential. And knowing magnetic vector potential, we could find E and H. We had two methods of doing that. One of them was more complicated, but it was valid both in the near field and far field. One of them was dedicated to far field zone. And for that, we essentially use plane wave relation. So this is going to be the main one that we're going to be using through this course. But for this lecture, I'm going to show also one example using that so that you can connect these two. But this would be really the focus of our course. We are mainly concerned with what's happening in the far field. Now, so let's start trying to use this to see what's going to be, how can we take advantage of this. So the first example that I want to perform, for example, here would be, for example, an open-ended transmission line. Imagine you have a transmission line and this transmission line is essentially open-ended. So you have open circuit here. So this is our transmission line right now. Now, assume that I have an AC source connected to that. That's a time varying signal, so that's appropriate for our discussion. But then I'm now want to ask you what would be the current on this structure. And the reason I'm asking for current, remember, current is essentially the most fundamental thing when it comes to our discussion of radiation. Remember, we had accelerated charges in the very first lecture. Then we connect accelerated charges to time varying currents because that's more practical for us as electrical engineers. So now, if I want to know the current here, this is open circuit. So essentially, I'm dealing with zero current at the end because it's open circuit. And if you're not careful about the fact that this is transmission line, so the length is comparable to wavelengths, you would essentially say the current everywhere is zero. But that's not correct if it's a transmission line. So if it's a transmission line, you get current like that, and this is going to be, for example, one wavelength in the structure where you have your full cycle. So and remember that this is your current, and remember, if it's not a transmission line, that means this thing is tiny with respect to wavelengths. So if it's tiny with respect to wavelengths, you're probably just looking at something very tiny like that. And if it's tiny, if it starts from zero, it can just do a little bit better than zero after that when it's tiny with respect to wavelengths. Therefore, that's why we can say the current everywhere is zero. But if it's comparable to wavelengths, you get like currents like that. And if you look at this situation, of course, if I assume this is positive, I can say, for example, positive current in this direction. This is negative current in this direction. And whatever happen on the top wire, in the bottom wire, I'm going to have the opposite effect like this. So if this is 1 lambda, this is essentially the current on my 1 lambda here. Current this way, and exactly opposite in the other wire. Now, if you look at this structure, my purpose here is to calculate A for this structure in the far field. I want to tell you something else before I go to that, and is that by definition, in transmission line, these two conductors are very close. So the way that I plotted them, you may say, okay, there is a good separation between them. But remember, this is just for demonstration. But by definition, the two conductors of transmission lines are extremely close to each other. So they're almost touching. So now, if I want to calculate what's happening here, I essentially need to perform the integration for A. So let's write the integration for A. A was mu naught 4 pi j r prime e to the power of minus jk r minus r prime r minus r prime dv prime. Now let's first focus on this r minus r prime that I have in this fraction. And if you remember, I essentially call this transfer function of free space. More technically speaking, people say this is the Green's function of free space. But let's focus on that. Now, if I make a coordinate for myself, for example, if I say, let's assume this is my coordinate, maybe let's assume that. And then we consider, for example, these two pieces of wire here, one of them here, maybe the other one here. Now, where is R? R is observation point. Now, let's assume that you are dealing with the far field, for example. Or relatively, I mean, it doesn't have to be far field in this case, but let's assume it's far. So this is your R, this is the observation point. And what is your R prime? R prime is a vector that spans over the current to get the different components of this current. For example, if I zoom in a little bit here, this is my current here. So for example, let's say this is Y, this is Z, this is your X. So if this is Y, this is your Z. Now, what is R prime? For example, if you think of this current as so many elements of current along, then this could be, for example, your R prime. Now you're covering this piece of current here. Now this is also your R prime. Now you're covering this piece of current here. Now this is also your R prime because you're covering this piece of current. And that's why we have integration over prime coordinate, because we want to get the effects of all these small pieces of currents in the observation point. So when you have summation of currents, you think about it this way, that you have so many tiny currents that compose the actual current, and then you go one by one and you calculate their effect, and then you sum them up, and that becomes your A at the observation point. So A at the observation point. So essentially R prime spans the domain over which you have current. So this is your R prime. Now, if these two are extremely close, so that essentially means they're almost extremely close to the origin. I couldn't plot them like that because you wouldn't see that, but think about it, very close to the origin. They're very close to each other. So if I make an arbitrary R prime like that, and if I find R minus R prime, this would be my R minus R prime. So this would be my R minus R prime. And if you make this R prime, if you think of this wire to be very close to the origin, in fact, R prime is so tiny that this R minus R prime is essentially the same as R. Compare this line from here to here with R minus R prime, from here to here. So these are extremely close to each other. So that's why when these two wires are so tiny, so close to each other, then you can approximate R minus R prime with just R, because R prime is so tiny. So essentially here I can say for this transmission line, R minus R prime, think of R minus R prime as just R. Then what's going to happen if I do that? Then I'm going to have A R becomes mu naught 4 pi j r prime e to the power of minus jk r divided by r dv prime. And now this is amazing for me. And the reason it's amazing is that, remember, integration is over prime coordinate. Prime was the coordinate over which I have my sources, source being currents here. So, and this e to the power of minus jkr divided by r had r prime, so it was part of the integration. But now that it does not have r prime, I can just take it out. And that becomes mu naught 4 pi e to the power of minus jkr r j r prime dv prime. Something that I should have mentioned in the previous lecture, but I'm mentioning it right now. Remember that J has a direction. Of course, it's a vector, and A shares the same direction with J. So these are the same thing. And make sure to look at this from also vector point of view, that this is a vector, this is a vector. Now, so this is my what I have here. And now this J is, of course, very general. For example, you can have volumetric current, you can have currents on a surface, and you can have current on a line. So this is different variation. So this is written in a way that covers different things. So it could be, as I mentioned, for example, a current that's flowing from a cross section. Could be current that, for example, flowing on a surface like that, or it could be just a current on a wire. So if it's a current on the wire, then I need to write that as this is now just a current on a wire with a direction. And now my volume essentially becomes length, because I said this is a current on a line. So instead of dV prime, I'm going to write dL prime. So as you see, for this specific case, this turns into this, because my current is current on a line. So the element of integration would be the element of length. So this becomes the situation that I have. Now I need to integrate that. So I need to integrate that. And if I integrate that, what do I get? If this is your I, the top wire is in this direction, with y hat, this would be essentially I with negative y hat, because you're going in the opposite direction. So if you start integrating that, what do you get? So the things that you're gonna get would be mu naught 4 pi e to the power of minus jkr r integral. Now, before I write that, I probably need to write something for this as well. So when you are taking the integration, you have some limits for your integration, of course. And in this case, as you see, my limit of integration is over this and over this. So when I'm calculating this integral, I need to write that integral. So I r prime dl prime, maybe for the top wire, plus I r prime dl prime for the bottom wire. Now, each of them is going to give me one answer. And remember, the limit of integration here, if you pay attention to the way that I plotted the wire, the length is along y. So essentially, instead of having dl, I could change my dl with element over y. So it's essentially, this is my dy, or you may call it dy prime. And then the limit of integration is the length of this wire here. So you could say, for example, the total length is L. Total length is L, and then you need to start performing your integration. But you know that the result of this integration and the result of this integration, they're going to cancel the effect of each other, because they're exactly opposite to each other. So whatever is the answer for this one is going to be the answer for this one, but with a negative sign. Therefore, these two going to cancel the effect of each other, and then you get 0 here. So as soon as you get 0, that means your A becomes 0. When A becomes 0, that essentially means that your E and H in the far field also becomes 0. So you don't get any radiation for that. So what do you learn from this is that when you have two currents that are very close to each other, like a transmission line, by definition, these conductors are close, and you have opposite looking current, then they essentially tend to cancel the effect of each other. And therefore, we need a mechanism to somehow take that into consideration when we are making our antenna. So when you are thinking about making your antenna, you need to somehow take care of this issue. Otherwise, your A become 0. And transmission lines are very important here because often antennas can be thought as the transition device between transmission line and free space, or to be more accurate, transition device between guided waves on one side. These are guided waves here. So you have electric field bounded between the two wires like that. And so between guided wave and free space wave. So you need to somehow take that into account. So that's what we need to do, and we're gonna do that. But this discussion was for you to understand that what's the issue here. And the other thing I probably, it's good that I mention it here. Look at the way that I plotted the current. I said the current is in this direction, this current is in this direction. Of course, I chose that randomly, and it really doesn't matter because remember, this is an AC source, for example, at 1 gigahertz. So this goes ups and down. For example, at one instance, this is high and then down, and then in a different time, this could be like this. So essentially, these would be reversed. But the point is, as soon as this is reversed, this is also reversed because that's essentially your transmission line. So the direction that I choose does not matter. It's the relative direction between them that matters. So that's our discussion based on magnetic vector potential, that why these transmission lines do not radiate for us. So now let's see how we can make them radiate, and that brings us to the first type of antenna that we want to discuss, dipole antenna. But before going to details of dipole antenna, I'm just using dipole antenna as a mechanism to elaborate on a magnetic vector potential more. So officially, we're gonna have more discussion on dipole antenna, but we're just using dipole antenna here to get to our discussion on magnetic vector potential. Remember, this is the extremely important tool for us, this magnetic vector potential. Okay, so we realize that when we have this open-ended transmission line that we had, so this is open circuit. So if I just plotted, for example, one wavelength over that. If this is positive, then this is negative. Remember that in the bottom you have exactly opposite. So this becomes this way, and this is this way, this is this way. So this is essentially the currents in this transmission line. When you are looking at these structures like that, you may get confused that how come this is the type of currents and things like that. This is just two pieces of wire. But I want to remind you that essentially these transmission line, there are two wires, but when the length is comparable to wavelengths. If the length is comparable to wavelengths, this structure is essentially like this. If you go back and review the courses on transmission line, you see that this is like this. This is the structure that we have, and it just goes on. If we have some loss in the transmission line, we need to add resistance. But if you look at this structure is open circuit, so I call this open circuit here, and this is my source here. So I plotted like that. Yes, this is two wire, but we have some hidden inductor and capacitor series that we are not showing here. And this is the reason that you see sometimes current distribution that it may not seem intuitive to you because you are not taking this into account. If you somehow have this picture over here when you are thinking about this transmission line, then it makes sense to you much better. So that's if you remember from your transmission line course, we call these PUL inductance and capacitance. So per unit length inductance and per unit length capacitance. And then we use these inductance and capacitance to find the characteristic impedance of transmission line, which is often 50 ohm in our applications. So anyways, that was our open-ended transmission line. So, but now what we're gonna do is that we're gonna take some part of this. For example, let's assume from here, we're gonna take this. So let's call this point A maybe. Let's call this point B just below that. And then we start turning from this the wire from this point and this point. So we're gonna bend the wire with respect to A. So essentially, what I wanna show you here is that if I have a piece of wire and I have point A here, I'm gonna start bending this piece of wire upward, and if this is my B, I'm gonna bend this piece of wire downward. So this is what I'm gonna do with that. So this is my purpose. So let me have maybe a focused plot here so that you can see it better. So this is my open circuit at the end, and this is my point A, this is my point B. Now I'm asking you, what is the current at point A toward open circuit? You agree with me that this is the current that we chose, so this is my current here. Now, what is the current from open circuit to point B? It's this direction. So this is the direction of that current. So these are the two directions, and of course they cancel the effect of each other based on the discussion that we have. Now, if I take this piece of wire and if I bend it upward 90 degrees, what do I get? So I get my point A here, and this current is gonna go up. So this current is gonna go up like this. And of course, when it reaches to the open circuit, it's zero. Remember, the current needs to be zero at the open, right at the open circuit, not within the transmission line. Right at the open circuit, it needs to be zero. So this current starts from here, and it's zero here. Now, if I now take the same thing and bend it downward, then this current is going to go downward. But pay attention to here that if this is your current and you're bending it this way, the current is going to be upward, like that. Now, let's see what happened. I had two currents that they were canceling the effect of each other. Now that I have two currents that they are helping each other. So this is really what happened here when I did that. So to repeat my discussion, let me make use of these pens. So imagine the tip of the pen is the direction of the current. So for this, I'm going to use this pen. And because this current is this way, I'm going to use it like that. So this is essentially the currents that I have. Now, what I'm going to do is that I'm going to take this current, which cancel this current right now, and I'm going to bend it 90 degrees like this. Now you see this current is upward. Now I'm going to do the same thing with this current. You see now both of them are upward, so they can help each other in the A equation. So again, to tell you about A is mu naught 4 pi j r prime e to the power of minus jk r minus r prime dv prime. So if you ignore this part, which you shouldn't, but for this specific case, that's fine if you ignore it. If you ignore this part, as you see, A is essentially the summation of J, but not summation of numbers, summation of vectors. So if you sum these two vectors, you get zero. But if you sum these two vectors, they're actually helping each other because they're in the same direction, right? And the reason we said we ignore this because we are assuming that the antenna is small in this case, so we can ignore it. But otherwise, this also matters a lot. This is summation of J vectors, but weighted with these coefficients. So essentially, this becomes my dipole antenna. So dipole antenna is essentially evolving from this antenna, that you have two pieces of current that pointing in the opposite direction. you take one piece of current, you bend it upward. So this current here goes up, and this was the other current that you had, and then you also bend this like that, so the directions become exactly the same. Now, of course, as you realize here, this is the current in the open-ended transmission line. Now, if you bend, current might change, but it has been shown that this, you can assume that the current is relatively stays the same, so you can essentially use that. But remember that if you do something to the transmission line, you cannot automatically assume that everything is the same, and it's just the direction of the current that's changing. Uh, but here we assume that this approximation is acceptable. So that's our dipole antenna. Now, with this dipole antenna, I can now go and find this A vector at the observation point R. So to do that, I'm gonna have my dipole antenna, and I'm gonna plot it more appropriately because these two things should be very close to each other, their transmission line. So this is, in fact, a good plot showing that these are transmission line. I plotted like that to give you the idea. So if you look at this point, the current goes from 0 to something. So essentially the same thing here. At the end should be 0. It goes to something, and then the same thing here. This is also the current here. So it's from 0 to something with the negative sign because it's the opposite direction. But now that you bend it and the directions are the same, so it goes from 0 again to here. So this is your current distribution. At the end, there it's 0, and it should be because it's open circuit right at the end. And then it rises because it's a transmission line. The length is comparable to wavelengths. It rises, and the same thing here, but with the negative sign, but you make the direction okay. So this becomes essentially your current. So current starts from minimum, and then as you get to the transmission line, it increases. So now this is what I want to work on. But before doing that, I still think this might be right now complicated. So I'm going to make an assumption, and this is my assumption right now. So the assumption that I make is that I have a dipole antenna, and the current distribution on the dipole antenna is uniform. So the current everywhere is the same. So this is my current, I naught. So if you compare it with this practical case, the current goes to 0 and then rises to maximum, again 0. But if I say the current is the same everywhere, this somehow not practical, because we know that this dipole is coming from this open circuit transmission line. So if it's an open-ended transmission line, current definitely has to go to 0 on the two ends of dipole. So if I say the current is uniform, perhaps I'm missing something. So that's one thing here. So, but this is what we do, and we call this dipole antenna infinitesimal dipole antenna. And I'm going to tell you a couple of reasons later on why we're using this type of dipole antenna. So infinitesimal dipole antenna, we assume its length is very tiny. So for example, length less than lambda by 50. So this is the total length. Lambda is the wavelength, so it's smaller than lambda by 50. So it's very tiny. Now, but I want to make a point here that if you have an antenna and you want this type of current distribution, this is not practical because at the end it was open circuit, so it has to go to 0. So a way around that is by top loading the antenna. So I'm just going to mention briefly, and then we come back to that later on. So you see, if I have a dipole antenna, for example, and if I put, for example, metallic disc here, now, you see here, this is not open end anymore. If the current go here, it's not open end anymore. They can actually flow on this metallic disc here. So if I do that, then the current, perhaps instead of going to 0 here, the current at the end can a little bit rise. So it could be like that, for example, because it doesn't have to go to zero. And this is called top loading of the antenna. So the current can rise, and therefore I may get something like this. But in our discussion right now, we are essentially ignoring top loading, but we assume that current is uniform. But if you want to make your current uniform, my point here is that you need to do something about that. One method is top loading to have a situation that current doesn't need to go to zero. So that would be a different discussion for us. So keep that in mind. So when I say current is uniform, remember my limitation, and I'm ignoring top loading here, but you could do that. The other thing that sometimes confuses people is that when I say current is I naught, I've seen that some people think current is perhaps 1 amp. But remember, when I say I naught, I mean phasor. This is a phasor because even with 1 amp, we cannot get radiation. 1 amp is DC. And you don't even have transmission line. So this is a phasor essentially. So when I say I naught, if you want to know your current, you should say real part of the phasor e to the power of j omega t. So this is essentially what you need to calculate. And if I assume I naught is real, then I of t becomes I naught cos omega t. So when I say this is the current is I naught, and I show it with that, remember that doesn't mean that current is always flowing upward. That only means current is, if you look at it, for example, at time equal t, the current is flowing to the top together. Now, if you change the time, the current may reverse the direction, but the key thing here, that would be together again, because you have a cos of omega t, it changes the sign. So if you look at the current at a certain time, they're doing this. In a different time, they're doing this. So that's essentially the current situation here. So when I have these two arrows, don't think that the current is always upward. That's not the case because this is a phasor. And when the currents are doing this, we call it the current are in phase. So whatever this current does too, and that's the important thing here. So this is a phasor. I want to emphasize that we are dealing with phasor here. So anyways, so I have that now. And then from this equation point of view, this is fantastic because now I turn canceling current to two currents in phase. So I could say out of phase current, I turned it into in phase. So I went from out of phase, you could say out of phase by 180 degree. Remember, 180 degree, when you are out of phase, why did I say 180 degree out of phase? Remember, e to the power of j pi, according to Euler equation, is cos pi plus j sine pi, and that's -1. So if I take this current here as I, now if I take the other current, the red one, as the same current I, but now I apply phase of pi. So e to the power of j phase, and phase is pi. So if this current is I, this current would be I e j pi, and that's my phase difference between these two currents. So you can think of I as I e to the power of j0, and this is I e to the power of j pi. Remember, j0 is 1. So now, if you look at these two currents, because j pi e to the power of j pi is -1, this becomes -I, and of course, e to the power of j0 is 1, so this is I. Now, this is exactly what we have in circuit theory, I and I minus I. And this minus takes care of the direction for us. So when I say out of phase by 180 degree, or simply out of phase, I'm essentially saying their opposite direction. But now these two currents are in phase. For example, if this is I e to the power of j anything here, theta, this is also I e to the power of j theta. So we call it, yes, these are in phase. So that's the situation that we have with this one. Okay, so let's continue our discussion. So let me remove this stuff from the whiteboard. Okay, so let me have a coordinate because I want to calculate this. So x, y, and z. So let me assume that I have my dipole antenna along z axis. And again, I have my two arrows here to say that these two currents are in phase, same direction. So, and I'm assuming that this is z equal L divided by 2, and this is z equal minus L divided by 2. So the total length of the dipole is L. And so, and I'm also assuming that the current over the dipole is uniform. So I as a function of z is I naught. And this is my phasor that I discussed earlier. So this is my current. And if we are considering current as vector, as here we are considering current as vector, I can have a vector sign here. And the direction of current is z hat. And you might say again, okay, Puyan, you mentioned that the current could also be in the minus z hat direction. Why this only shows z hat? Because again, you're looking at the phasor. If you convert that to time, then you get I naught cos omega t, assuming that I naught is real, z hat. Now, cos omega t can change sign, therefore it could be minus z hat too. So that's my phasor. So the calculation is in phasor. That's why we have our z hat over there. So this is my current. And now I need to perform my calculation. But before doing that, let me emphasize here that this is an infinitesimal dipole. So the current is assumed to be uniform. So, and then the length of the dipole is so tiny. So the length, let's say, less than lambda by 50. So when the length is so tiny, then what happens is that your R prime is again so tiny compared to R. Because let's review our R prime again. So this is my antenna here. And I'm going to show antenna with a very tiny antenna because this is really what's going on here. This presentation here is just for clarity. This is my antenna, very tiny. So what would be my R prime? R prime is the vector that connects origin to the different points on the dipole. Now this dipole is on the Z axis, so I slightly shifted so that you can see. So R prime, for example, would be this vector. This tiny vector here is my R prime. Now, if R is away from the dipole antenna, like this, for example, in this case, it doesn't even have to be in the far field because R prime is so tiny. What is the maximum of R prime, you think? If the total length is lambda by 50, the maximum of R prime here would be lambda by 100. So this would be maybe lambda by 100 z hat. So this is going to be very tiny. And if this is your R, this is become your R minus R prime. As you see, R minus R prime is practically the same as R in this case. Because of that, I can again make the assumption that this factor that I have here for this example is e to the power of minus jkr r. And this is consistent with my assumption with transmission line, because in transmission line, these two pieces of wire were also very close. So I made the same assumption there too. So here I would do that. And I want to tell you that that's the only antenna that we are making this assumption for in this course with an antenna which is related to this concept. But for most other antenna, we're using better approximation than this. So, and you're gonna see that later on. So, but for this antenna, we're gonna be using this one. So let's move on with that. So if I start my calculation, I'm going to say A at observation point R is mu naught 4 pi. Then I can take it out from the integration. And then now the current density is essentially my current on a line. So I'm just going to write I Z, or you could write Z prime to be consistent with the prime coordinate. Usually prime coordinate, we are using it for to indicate that we are integrating over source. So if you prefer to be consistent, you could also use Z prime. So it's just a standard method that's saying that we are integrating over the source, which is the current. And then your integration here would be integration over lengths. And as you see, the tiny lengths here would be your dz. So the element over the z axis. And if you want to again be consistent, you may want to write dz prime. So that's our integration. I'm only missing one thing. This is a vector, so I need to put vector here. So you may put z hat. So because z hat is my vector. So at this point, sometimes I get the question why you didn't write z prime hat. And the reason is, I mean, z prime hat is somehow meaningless because z hat is an established direction that does not change based on the fact that you call something prime coordinate or non-prime coordinate. Z hat is Z hat. So we keep it at Z hat. If you want to write Z prime hat, then at the end you have to change it to Z hat because Z hat is the established direction along Z axis. That's for us to remember that we are integrating over source. But this vector is a fixed vector in one direction. Some vectors, as we're going to see, they're not constant vector and they keep changing. And we're going to talk about those vectors. And in those situations, we keep the prime coordinate. But z hat, x hat, y hat, we just write them as z hat, x hat, y hat. And now the limit of integration, of course, is from minus L divided by 2 to plus L divided by 2. So that's my limit of integration. And I also know that my current is I naught. So I can just remove that and write I naught here. And this is constant, and you're integrating this over lengths. So the result of integration would be I naught times L2 minus L2. That would be I naught L. So I can just directly write the result as mu naught 4 pi e to the power of minus jkr r. And this is going to be I naught L. And that's going to be my z hat. So this is my A, essentially here. Now, this is my A, and I want to make a few points here that you can observe it better. So one thing that I want you to pay attention here is that we have this I naught times L. And if you pay good attention to this, you realize that this I naught times L is the area under the curve. Now, what do I mean by this? Remember, this is my dipole, and I assume the current on the dipole is uniform. So everywhere I go, I'm assuming I have I naught. So this is essentially my I naught. So essentially here I naught, here I naught, here I naught. So this is my I naught. This is different than my first assumption that I mentioned the current is like this. So current is 0 and then, so it's half a cosine. But here I'm assuming it's uniform and it's I naught. And remember, the length of the dipole was L. So if you calculate the area under this curve, this is a rectangle and you get I naught times L. And that's my I naught times L over here. So that's one thing to remember. The other thing that you may notice here is the presence of this, e to the power of minus jkr divided by r. That's essentially, we had earlier discussion on this, that this essentially shows that the wave is propagating along the r direction. Remember the way that I did that? I said if you convert that to time domain, you get something like cos omega t minus kr for this one. So t increases, I mentioned that r increases. So you're expanding in a spherical fashion. So that's also another thing to keep in mind. And we're going to come back to more discussion on this. Now, this is my A, and my A is in the direction of Z hat. Now, remember, in antenna, we use a spherical coordinate most of the time. But here, I mean, of course, when you calculate A would have the same direction as J. Your current is in the Z direction, so A becomes in the Z direction. But in the remaining part, you essentially need to work with a spherical coordinate. And if you want to do that, you usually need to convert this, which is in Cartesian coordinate, to a spherical coordinate to be able to use the methods that we described in the previous lecture. Now, how do you convert a Cartesian coordinate to a spherical coordinate? We have a formula for that, and this is a formula that you will be using in this course. Let me write the formula. So let's assume that one side I have my spherical coordinate. So a spherical coordinate has three components: AR, A theta, and A phi. So this is the three components of A in the spherical coordinate. Now, what I know here is the three component of Cartesian coordinate: AX, AY, AZ. So now I'm asking myself that I need a matrix that takes the Cartesian coordinate and convert it to a spherical coordinate. And that's the matrix that you are familiar with your previous courses. I'm going to write it for you, and then we're going to be using this matrix in this course. So this side, for example, in this particular case, what is your AX in this particular case? Your AX is in fact 0. You don't have any AX. It's A is in the Z direction. What is your AY? You don't have AY. It's 0. What is your AZ? This is your AZ. So the whole A is AZ, Z hat. The Z component of A is called A subscript Z. So this is your AZ. So I have only this for this antenna. Now, let me have my matrix here. My matrix, of course, becomes in terms of angles, theta and phi. So that becomes sine theta cos phi, sine theta sine phi, cos theta cos phi, cos theta sine phi, and minus sine theta, minus sine phi, and cos phi, and 0. So this is essentially what you have. This is the conversion matrix that takes the Cartesian coordinate. It gives you back your A component. Now, let's get our A components back. So to do that, let me remove this part. So what would be your AR, for example? AR would be this times 0, this times 0, cos theta times AZ. So my AR becomes cos theta times AZ. So that's my AR, cos theta times AZ. So now I want to just make sure that you understand what's going on with this AR. So remember that A is in the Z direction, right? So A is in the Z direction. So assume that I have a coordinate X, Y, and X, Y, and Z. And this is a vector in the Z direction. Now, does this vector has an R component? Remember, R hat means radially outward. So if I plot in the different coordinates, these are all R hat. These are all r hat. It's just radially outward. So z hat, which I have here, qualifies for r hat. So remember, this is what you have essentially. If you have a z component, you could have an r component exactly because of this. So r hat means radially outward, and z hat is one specific form of r hat. So that's why az contributes to ar. Now, let's continue with that and have a theta. A theta becomes, so this times this 0, this times this 0, and you get minus sine theta az. So you get minus sine theta az, so that's your A theta. And then what's going to happen is that you need to check for your A phi, and your A phi becomes this times 0, this times 0, 0 times az. So this is your A phi, 0. So now you have the three components of A in the spherical coordinate. So this is the three components of A in the spherical coordinate. And now you can use equations to find E and H in different regions. Now, based on the fact that I don't have time, I'm gonna stop here at this point and then continue with exactly at this point in the next lecture. Thank you.